as we begin to work on complex numbers, what we can do is we can actually graph complex numbers, and it looks a lot like the rectangular coordinates that you're probably used to, except instead of the x-axis and the y-axis, we switch it over to the real axis and the imaginary axis. So as you look at complex numbers, sometimes we call this a complex plane, by the way, but what makes something a complex number is if you have a real part with an imaginary. So the whole thought process is, if I'm starting at the origin, which is still technically like 0, 0, but you can think of that as 0 plus 0i. And one way that you can actually think about this is if we're adding a new axis to the number line. So the number line, we're so used to going right and left. So if I asked you to where part A is in this problem, it'd be 5 minus 2i. You go 5 units on the real axis, and then negative 2i, so down on the imaginary axis. I'm just going to label this part A, because that's the letter it's corresponding to. So where's the letter B at? Well, you go 3 units on the real axis to the right 3, and then 1, 2, 3, 4, 5, 6, 7 on the imaginary axis. And then C is negative 2 plus 6i, so left 2 on the real axis, because it's negative, and then 1, 2, 3, 4, 5, 6 on the imaginary. And then negative 4 minus I, 1, 2, 3, 4, but minus I would be down 1, that would be a letter D. 5i is simply straight up. That's letter E. And if it helps, you could go ahead and rewrite this as 0 plus 5i. So it's like the ordered pair right 0 up 5. Same thing with this last one, is you could rewrite this as negative 6 plus 0i. So you're just going 1, 2, 3, 4, 5, 6 units on the real axis to the left. So what you can do is you can actually answer a few questions like this. If we're just asking you to plot the complex number and think about where you're at, well, left 3 and up 5, we end up in quadrant 2. That's quadrant 2 over here. In case anybody's forgotten, quadrant 1's in the top right, quadrant 3 is in the bottom left, and then we finish up with quadrant 4. IV is the Roman numeral. And it's just going in order, starting counterclockwise, going this way. And that'll make more sense as we get into more difficult problems. So I'm kind of not a fan of how he explains this next section. I would actually do exercise 4. I actually prefer exercise 4. And the reason for that is when they talk about the modulus, they're talking about the distance from 0. Well, 0, as I mentioned before, is at the origin. And that's actually the definition of the absolute value. Absolute value is the distance away from 0. So if I were to do this problem and I plot the ordered pair negative 3, 1, 2, 3, 4, 5, 6, plus 6i is right here. Sometimes we actually draw an arrow to connect it from. And so the whole thought process is, if I made a right triangle in here, and what I'm thinking about is doing the Pythagorean Theorem, where this distance is 3. I know it's negative, but as far as the distance goes, it's just a positive, and then it's up 6. Well, I could set up the Pythagorean Theorem is equal to, I'm going to use M for the word modulus. And so the whole thought process, if I go ahead and write down the Pythagorean Theorem, is that you're doing 3 squared is 9, 6 squared is 36, and then you can square root both sides to solve that. Well, first of all, that's 45. And just a reminder on simplest radical form, because I do want you to practice that. That's 9 times 5, and 3 and 3. So the modulus in this problem is equal to 3 root 5. If you remember how we talked about doing this. So I would actually prefer that method of doing than, if I go back to exercise 2, how they just tell you to do this problem without really any prerequisite work. So again, the size, the modulus, it looks like the absolute value. So you might even hear me say, take the absolute value of this. But yeah, if you were to look at a problem that's 3 minus 4i, and you go right 3 and down 4, and you want the length of that axis, then it makes sense to do the Pythagorean theorem of 3, 4. And this is actually a Pythagorean triple if you've ever heard that phrase before. But if you follow this work, the absolute value of 3 minus 4i, well, that's equal to 3 squared plus 4 squared, which equals the modulus squared. So to solve for it, you can square root that. Well, 9 plus 16 is 25, and the square root of 25 is 5. So double check my arithmetic. Don't just believe that this is right. For instance, I know a lot of Pythagorean triples. And if you don't know what I'm talking about here, you should do a quick internet search on some of the special. So I already know that this answer is going to be 13. But there's a lot of them, 7, 24, 25. And any multiple of these are also. So like 3, 4, 5, if you double every one of those numbers, 6, 8, 10 is another Pythagorean triple. So that always works. But again, double check that my answer is correct. Go through the work, whether you do the Pythagorean theorem or you work it out the way this says. I'm doing 12 squared plus 5 squared. And notice you just ignore the I because, well, you'll get the wrong answer if you do I squared and you try to subtract. Anyway, 144 plus 25 is 169. The square root of 169 is 13. So this last one, definitely not as easy. So if you solve this, you square both, so it'd be 16 plus 4. We're looking at the square root of 20. Well, we can get a pair of 2's out of that. 4 and 5, 2 and 2. Scroll down just a second. And so the correct answer would be 2 root 5 is what I'm looking for. But again, you can either follow that formula or you can do the Pythagorean theorem. But you need to make sure you know how to find that answer, whatever works for you. So this next one, what's important is that you're only adding and subtracting the real components with real components and imaginary with imaginary. So what I'm talking about is if I'm adding two things together, you can only combine the real parts with the real parts. So negative 2 plus 6 is 4, and 7i plus 2i is 9i. And if it helps, think of them as just, how do I want to phrase this? As variables, that if you did 7x plus 2x, the answer is 9x. Same with the next one. 8 and 12, we can combine those together. Those are like terms to be 20. And 4i plus negative 1i is 3i, just like any variables. Now what's tricky about the next one is I always encourage students to distribute that minus into the problem. Didn't have that on an A or B, so it's minus 2 and then plus 7i. So 5 minus 2 is 3. 3i plus 7i is 10i. Same thing with the next one. It's just, me being me. That's subtracting a negative is plus, and then minus the positive is going to be a negative there. So negative 3 plus 8 is 5, and then 5i minus 2i is 3i. So the thought process, though, is if we were adding two pieces together, we could find out what quadrant we're in. So in case you didn't know, the word sum means add. So you could go ahead and just add them together. I'm not sure why I'm writing it this way, but I am. And 6 minus 8 would give me negative 2, and 2i minus 5i is negative 3i. So now you can actually figure out, okay, that's left 2 and down 3 on my imaginary axis. to figure out that we're in quadrant 3. Now, if anyone's curious, what you could actually do is plot each one of these individually. So 6 plus 2i, is this kind of, and you might learn this about vectors. So from this point, you can actually move 8 on the real axis. So from this point, moving 8 in the left direction would take us back over here, and then minus 5 in the I direction would be 1, 2, 3, 4, 5. So adding those vectors together would end up with the resultant down here. And that could also confirm your answer. So there's a lot of connections, a lot of visualizations you could look at. So this last one, if you read between the lines, is basically asking furthest from the origin would be the largest modulus. So start to get used to this word, but it's basically the absolute value needs to be the largest, because there's some close answers. If we looked at, go ahead and put my absolute value symbols in there, and just see which one's the biggest. Okay, so this one's going to be 5, so it's not very large. Just because if you go into more of the other ones, we're looking at the square root of 4 squared is 16 and 49. Pretty large, although let's look at this one. It'd be the square root of 4 plus 64. All right, so that's the square root of 68. And comparing it to this one, that would be 55, 65. And then this last one's also pretty small. 1 plus 36 is 37. So I'm going to commit to option 3. I think that one's the largest. And you should be ready for the homework now.